Hello students, how are you? So in the previous class, we have learned a very important definition of delta U, which says that delta U is equals to heat change at constant volume. And also for enthalpy also, we learned a very important formula that gives us that enthalpy change at constant pressure is equals to the heat exchange during that process. So we can say that delta U is equals to QV and delta H is equals to QP. Further, we also know that QV is equals to CV delta T, where C is the heat capacity, okay, at constant volume, and CP is the heat capacity at constant pressure. So we can now we can directly relate delta U is equals to CV delta T and delta H is equals to CP delta T. So these two formulas are very important. Now using these two formulas, we have derived a very important formula, which is CP minus CV is equals to R. Okay, and before that, we just move on to a more important formula. So these are the formulas that is important. So I'm making a quick revision of all of that. So which says that delta H is equals to delta U plus delta NGRT. Why I am saying that delta NGRT? So basically we are saying that we are talking about the change in number of gaseous moles. Okay, not any other mole, not just any other mole. It is talking about the gaseous number of moles that has been changed. So these are the four formulas that you should remember, and I will use it here. Okay, so I will just say that okay, this is this. So you must be aware about those. Okay, now we said that okay, we are done with this formula and all. Now we know we want a method. We want a method to just calculate all of this, right? So just by putting it in theories is not significant, right? So to make it more appropriate or to make it more handy, what do? We do experiments and calculate the values of each of these using these formulas that we have formulated. So for that thing, we have a instrument called as calorimeter. Okay, this calorimeter will help you to determine and will help you to admire that how these formulas are important. Clear? So what are we doing here? So basically with the help of calorimeter, we calculate the heat change. Okay, we calculate a heat change of a volume of a liquid. Knowing the heat capacity of the liquid in which the calorimeter is immersed and the heat capacity of the calorimeter, it is possible to determine the heat evolved in the process. So we will get back to it. So what does this mean? So first of all, there are two types of calorimeter, that is QV and QP. So for QV, we call it as bomb calorimeter. Okay, so if you are conducting your experiment in such an environment that the volume remains constant, then we call that calorimeter in which that environment is you can say produced. We call that as bomb calorimeter. If we do the same experiment at constant pressure, then the environment that is set up, it is done by the simple calorimeter. We don't have any prefix for that calorimeter. It is simple calorimeter. Okay. Now, so for chemical reactions, heat are absorbed at constant volume and it is measured at constant in a bomb calorimeter. So as I have told, so since we are keeping the volume constant in the calorimeter, so the calorimeter will be termed as bomb calorimeter, and the bomb or the steel vessel is immersed in a water bath, and the whole device is called as calorimeter. Okay, so the steel is immersed in water to ensure that no heat is lost to the surrounding. So I mean this thing. So this is your bomb that I'm talking about. So this is the steel cage that you can see. It is mentioned as bomb. So this steel cage is immersed under the liquid. Okay, and this liquid will make sure that no heat escape this vessel and go out of this vessel. Okay, clear? Now, next thing that we have here is a thermometer that is immersed in the liquid so as to know the temperature change that is going within the liquid. Okay, here is the oxygen inlets that we are dipping oxygen inside it, or we are pumping oxygen inside this vessel only, not outside this vessel, inside this bomb. And we keep our sample here. Okay, we keep our sample here and we fire. These are the firing leads. You can think it just of a device that is used to ignite this sample or to burn this sample. Now what is being done here, that we are keeping the volume constant. See, it is closed from the upside and we have supplied enough oxygen so that it is completely under great pressure. Okay, so this oxygen is under pressure. Okay, so that the volume change cannot happen. So this setup is there done, means it is just closed with a lid. We are putting in oxygen under pressure. So we are doing this all to ensure that the pressure the volume does not changes. Okay, so if you have a volume that is available for the gas or for the product to get to say expand, then the volume will change, but we don't want it to happen, right? So for that reason we are putting up a lead here so that the volume can be remain constant. Clear? So we take a combustible substance, we burn it in dioxygen in the steel bomb, and the heat that is involved, this heat will be transferred to this water. And why is the stirrer here? So the stirrer makes it sure that the heat that has been transferred from the calorimeter to the water is being evenly distributed. Okay, you will just think of it that it can be evenly distributed even though we don't do it, but still to make it properly, you can say, make it a more homogeneous heat. What do? We put a stirrer here so that the heat can be you can say it can be properly distributed. Now note that this stirrer rotates with a very slow speed, because if we do very fast rotation of this stirrer, then it would result in increase of the kinetic energy, and that would be stored in water as the heat. So we stir it very slowly just to ensure that the heat is distributed uniformly throughout the liquid. Clear? Now we have kept a liquid whose heat capacity is already known. Okay, now we are measuring the temperature, we have kept the volume constant, we are supplying heat to it. Now this thermometer will calculate the heat change. We know that the volume is constant, so whatever with the heat change we will calculate it. We know already the heat capacity. So what is the formula for heat change? So Q is equals to CV dt. Why I am taking it CV? Again, CV I am taking because your volume is constant. CV delta T, not dt, because we are doing it for a large temperature range. So CV delta T. So that will give you the heat that is evolved during the combustion of this substance that we have taken, right? So the same thing is written here. Under this condition, no work is done. So whatever with the QV that we calculate here, that will be purely equal to the internal energy. So that is the kick part here. So why are we keeping the volume constant? Because to ensure that since volume is constant, we know the formula for work done for both reversible and irreversible. Okay, we know that if we take same volume, means the volume is not changing, then you will get the work done is equals to 0. Clear? Now temperature change of the calorimeter produced by the complete cell is equals to QV, and by knowing the QV, how you will calculate QV? QV is equals to CV delta T, and thus QV will be equals to your internal energy change at constant volume. Okay, in this fashion you will calculate your whole, or you will utilize your whole setup to calculate your internal energy change. Okay, so this is your bomb calorimeter. This is your bomb calorimeter to calculate a delta U. Again, volume is kept constant. The heat that is evolved from this reaction, it is being absorbed by the liquid that is present here, and we measure the temperature change with the help of thermometer. We already know the heat capacity of that liquid. We multiply the temperature change with the heat capacity to get the heat that has been involved, and since it is done at constant volume, we call it as QV, and that QV is equal to the internal energy change, which is indulged when we have burned this species. Clear? Okay, so this this is this firing lead is here to just ignite it. Okay, so you should remember it is nothing but it helps in the ignition of this product. Next part is delta H measurement. Okay, what is it? Is delta H measurement. So how are we doing it? So in this case, what do? We don't seal it. Okay, rather than sealing it, we expose it to the atmospheric pressure, such that this atmospheric pressure confirms that your pressure inside the inside the container remains constant, because we have applied a constant pressure for that. Now we will call your heat change as QP, because in this case it is occurring at constant pressure or at atmospheric pressure. Now if you calculate Q here, the same way we have did it earlier, we will just to take a liquid and make sure the volume changes. Okay, so in that case we will calculate the Q, and that Q will be equals to QP, and we know our formula delta H is equals to QP. So it will give you what? It will give you your enthalpy change. Clear? Okay, next, a very important point is to mention here about the sign convention, right? About the sign convention. Now if I talk about the importance of sign convention, then I would say that if your QP is negative, right? If your QP comes out to be negative, and when it will be negative, when your T final minus T initial is negative. So when your T final is smaller than the T initial, I would say appropriately, then in that case, I would say that QP is negative and your enthalpy change will be negative. That will result in a exothermic reaction. Okay, so that would be a exothermic reaction. Whereas in endothermic reaction, heat is absorbed. Okay, heat is absorbed. Therefore, your reaction will be delta H will be positive. Therefore, it will be endothermic reaction. Clear? Got it? Now, this reaction is endothermic in terms of water because we are calculating it for water. But in case of the actual reaction that we are considering or that we are studying, that would be opposite of it. I mean, if QP is negative, it will be endothermic. Okay. And if QP is positive, that will be exothermic. So this is very important differentiation, right? So let us do a problem first of all. So what does the problem says? It says that we are burning 1 gram of graphite. Means our sample that we have taken in the bomb calorimeter is 1 gram graphite. Clear? Next is it is burnt in a bomb calorimeter. So therefore your volume should be constant because we take bomb calorimeter, then we have to keep the volume constant. In excess of oxygen at 298 Kelvin, temperature is given and pressure is given as 1 atmospheric pressure, and that is happening according to this equation. C plus O2 is giving you CO2, where the C is in the form of graphite. So don't confuse it with any other. So diamond will also have the same C. Graphite will also have the same C because they are all allotropes of carbon. So what do we doing? We are taking graphite, which is C. We are reacting with oxygen to give CO2. Now during the reaction, temperature rises from 298 Kelvin to 299 Kelvin. Temperature change is clearly mentioned. Okay, one more very, very important thing. So whenever you do such thing, suppose you have taken, it was given instead of Kelvin, it was given in degree Celsius, right? Then if you take out the difference, both in Kelvin and degree Celsius, the difference would be same. Just try to do it. What is 298 Kelvin in Celsius? So 273 plus minus 298. So 298 minus 273 will give you 8 minus 3, 5 and 9 minus 2, 9 minus 7, 2. So 25 degrees Celsius. So we are going from 25 degrees Celsius to which temperature? To 26 degrees Celsius. So that if you just subtract 26 minus 25, it is 1 degree Celsius. If you subtract 299 minus 298, it will again give you 1 Kelvin. The value is absolute value is perfect. Okay, it will not change. So why I'm saying it, some students do the mistake of doing conversion after the difference. Okay, after taking the difference. So what do? They take the difference 299 Kelvin minus 298 Kelvin. So it will come out to be 1 Kelvin, and then they convert it into degree Celsius, that is subtracting minus 273. So that will give you a wrong answer, right? You can't do this. So what you have to do, if you are taking out the difference, then that thing is fixed, that okay, this difference will be same in Kelvin, in degree Celsius, or in other part. Clear? So my whole point is, do not convert if you are taking out the difference. Clear? Okay. So this will come out to be 1 Kelvin. If the heat capacity of the bomb calorimeter is 20.7 kilojoules, so now we are taking the bomb calorimeter heat capacity also. Okay, then what is the enthalpy change for the reaction? So we have to take the enthalpy change for the reaction. Clear? So let us get back to the formula. What do we need? We have to calculate the enthalpy change. Okay, we are not given here a normal calorimeter. We are given here a bomb calorimeter. Okay, so first what we will do, we will calculate delta U. Okay, so let us solve step by step. So it will be very fun to solve this question. So first of all, I will calculate your QV, that is your heat capacity at constant volume. So that formula is very simple, CV delta T, right? It will be CV delta T. So now, as I have told you, that this thing will be just opposite. Whatever may be the heat that is released by the system and absorbed by the water. So we are calculating your Q in terms of water. So in actual meaning, it will have the opposite sense. Okay, so think it on this way. So suppose if your system is releasing heat, so it will be exothermic, or it loses energy, where the surrounding is gaining heat, so its energy will be in positive. So sign will be just opposite of each other. So the Q that you will get here, the system will get or lose that opposite amount of energy. See. So if you calculated Q here, you got it as minus 20.7 kilojoules. So this is the Q that is being gained by the water. Okay, and for that we have calculated it out. Now here negative sign indicate the exothermic nature of the reaction. So that is the reason we are taking a negative sign here also against it. So what we have done, instead of converting it later, we have taken a negative sign in the start only. That okay, this is the amount of heat that is gained by the water. So the negative of that will be lost by the system. So we have taken negative sign, and that has given you 20.7 degrees Celsius. Clear? So this is for delta U for 1 gram of graphite. We have calculated your delta U. But if you go back to the question, we don't need delta U. We need delta H. That is our enthalpy change. How you will calculate it? We have a formula here. What is the formula? Delta H is equals to delta U plus delta Ng RT. So we will use that formula. Okay. Clear? Okay. So first of all, we will calculate the number of moles that is present in 1 gram of graphite. Okay, 1 gram of graphite is here. So this graphite is going and converting into CO2. So 1 gram of graphite, so if you calculate the number of mole, so for combustion of 1 mole of graphite, if you calculate it, it will be minus 2.48 into 10 to the power 2 kilojoule per mole. So what we have done here is that we have taken one mole of graphite. So initially we have calculated it for 1 gram. Now we have converted it for 1 mole because we need it in terms of mole. Okay. So for 1 mole of graphite, it will be minus 2.48 into 10 to the power 2 kilojoule per mole. Clear? Now if you go back to this equation, what is the change in number of gaseous moles? So you will make the silly mistake of counting the number of moles in a simple way, that it is 1 in the right side and 2 in the left side. So that will give you minus 1. So that will give you the completely wrong answer. Because this graphite is present in a solid form. Okay, it is present in solid form. Therefore, the only gaseous species that are involved are carbon dioxide and oxygen. So here is 1 mole, here is 1 mole, 1 minus 1, delta Ng will be 0. Clear? Delta Ng will be 0 here. Now delta Ng is 0. Therefore, we can use this formula. Okay, delta H is equals to delta U minus, since delta Ng is 0, we don't have to multiply it. Our answer will be this one directly. Now, why we have done this? Why we have used this formula? Because we have taken volume constant. Okay, we have taken volume constant, and since volume is constant, and we know that delta H is equals to delta U plus delta PV. Okay, since pressure, volume, all things are constant, therefore delta H will be equals to delta U. We have already derived this formula previously, right? That at constant pressure and constant volume, delta H and delta U are both equal. So with this, we have completed the calorimeter and we have done a problem on it. Okay. So thank you for your time. This was for today's class.